短く。
Now we would like to start the first keynote speech. The speaker is Dr. Makoto Kobayashi, the chairman of the organizing committee of the Third Hope Meeting, executive director of JSPS, honorary professor emeritus at High Energy Accelerator Research Organization, and Nobel Prize laureate in physics in 2008. The title of the lecture is Development of Particle Physics. Dr. Kobayashi.
Okay. Thank you very much, kind introduction. Okay, in this lecture, I plan to talk about the history of the particle physics. Particle physics is just one of the many fields of the science, and I understand that most of you are not working on the high energy physics, but I think that there are many features in the development of the science common to all the field. So it's desirable if you find some hint to your research from this history of the particle physics. Okay, particle physics was born around 1930, so that it has a history of about 8 years, and of course it's impossible to cover the full development in 1 hour or so. So the subject I'm going to tell you chosen at random, but I try to cover the major contribution done by the Asian scientist. So let me start with the birth of particle physics. Here we'll consider the 3 important works at the beginning of particle physics. The first one is the Dirac equation and discovery of the antiparticle. Okay. In the early 20th century, 2 important theories, special relativity and quantum mechanics, appeared. The special relativity is related to the property of the space-time and the kinematics of an object moving very fast speed as different from that of the classical mechanics. Anyhow, special relativity was developed without considering the quantum mechanics. On the other hand, the quantum mechanics aimed to describe the motion of the electron in an atom, and it was formulated according to the non-relativistic kinematics, at least in the early stage. In 1928, however, the Dirac tried to describe the relativistic motion of the electron in quantum mechanics, and he proposed the so-called Dirac equation as a relativistic extension of the Schrödinger equation, which is a fundamental equation of quantum mechanics. This is a Dirac equation for the free motion of the electron. In the Schrödinger equation, the wave function psi is a single component complex number, or if we take into account the spin degree of freedom of the electron, we can consider the psi as a 2-component wave function. Anyhow, on the other hand, in the Dirac equation, the wave function consists of 4 components, and alpha and beta, here the 4x4 matrix, acting on those 4 components of the wave function. I don't enter why this is a relativistic extension of the Schrödinger equation. The most important fact here is that the Dirac equation has a solution with a negative energy solution. Namely, the solution exists for the energy range not less than mc squared and not greater than minus mc squared. So the allowed range of the energy is something like this. And the positive energy solution are what we expect. So, but the negative energy solution are confusing, because in quantum mechanics, particle can jump by emitting the absorbing the photon. So the electron in the positive energy state will fall into the negative energy state emitting a photon, which means that there will be no stable positive energy electron. To avoid this difficulty, Dirac proposed all the negative energy states are occupied by the electron from the first. We call those electrons the negative energy C or Dirac C. The electron are the particle obeying the Fermi statistics. So if we assume that all the negative energy states are occupied, then the normal electron can fall into the negative energy state. From this interpretation of the negative energy solutions, we can draw a startling conclusion. If an electron is removed from the Dirac C, such a hole in the Dirac C would look like a particle with a positive energy and a positive electric charge. Lack of the negative energy look like a positive energy, okay? This is a familiar idea in the current material science, but let me remind you that in this case, this hole would appear in our vacuum, okay? So Dirac predicted the existence of the positively charged particle, and the particle should have the same mass with the electron. This was the first time that the humankind noticed the existence of the antiparticle. Soon after the Dirac's prediction in 1932, Anderson discovered this particle. And the cloud chamber exposed to the cosmic ray, he found this positively charged particle. He gave the name positron to this particle, and we are using this name today for the antiparticle of the electron. Okay, now in connection with the Dirac equation, I would like to mention about the Klein-Nishina formula, okay, which gives a cross-section for the Compton scattering. Compton scattering is the scattering of the photon and the free electron. The Klein and the Nishina obtained this formula for the cross-section in 1928, this formula. And this was immediate after the Dirac equation was proposed. And at that moment, the treatment of the negative energy solution was still unclear at that moment. Okay. An interesting thing is that the Klein-Nishina formula includes a negative energy state as an intermediate state of the perturbative calculation. Also, it was not mentioned in the paper explicitly. This is somewhat contradictory to the later interpretation of the negative energy state, that the negative energy state are occupied. The answer to this question are the following. According to the whole theory, we need to take into account the intermediate state consisting of two electrons and a positron, one positron, okay, three particle state. But inclusion of the negative energy state in the Klein-Nishina formula gives just the same effect with this three-body state. Okay. Dirac was aware of this fact when he proposed his whole theory. Okay. Yoshio Nishina was born in 1890 and died in 1951. After graduated from the Tokyo Imperial University in 1918, he went to Europe in 1921 and stayed at Copenhagen for many years. He wrote the Klein-Nishina paper when he was at Copenhagen. After he came back, he became the principal investigator in Riken, in Japanese Institute, and his lab became a center of the particle and the nuclear science in Japan. Okay, another topic I would like to mention in this connection is the electron-positron scattering. The electron-positron scattering is somewhat special because the positron needs an antiparticle of the electron. Namely that there is a contribution from the annihilation of diagram in addition to the ordinary Coulomb scattering type diagram. Calculation of the cross-section of this scattering was done by the Homi-Berber in 1935 in the study of the cosmic rays. The electron-positron scattering is now called the Berber scattering. The Homi-Berber was born in 1909 and died in 1966 in an air accident. He was born in Mumbai in India, and when he was 18 years old, he moved to England and studied at the Cambridge University, and he came back to India in 1939 for vacation, but the World War II was broke out, and he was forced to stay in India. He is regarded as the father of the nuclear program in India. Okay. So far, I talk about the Dirac equation, and the Dirac equation is certainly one of the roots of the particle physics. Now, the second important work, which is root of another aspect of the particle physics, is Fermi's theory of weak interaction. Radioactivity was found in the end of the 19th century. Through the study of the beta disintegration, a couple of the mysteries emerged. One is the energy spectrum of the emitted electron. If the beta decay, beta decay of the nucleus is an emission of the single electron, the electron should have the definite energy, while the observed spectrum of the electron is continuous and the energy is widely spread, distributed. Pauli gave a solution to this question by introducing a neutrino which conveys the energy but escapes the detection. Another question is that whether those electron and neutrino, where those electron and neutrino come from. At first, the question was probably, are they what do you say? Are they confined in the initial nucleus before the emission? It should be noted that for the people at that time, it was difficult to think that the electron is emerging from the system without the electron. Okay. So first they thought that those electrons might be inside the neutron from the first. In 1933, however, the Fermi proposed a field theoretical description of the weak interaction. This form of the weak interaction is called Fermi interaction, although this is not exactly the same as the original form proposed by Fermi. Anyhow, the point of the Fermi theory is that the electron and the neutrino are created at the moment of the interaction. Okay? And the neutron changes to the proton at the same time. Since the field variables are acting as the creation and annihilation operator of the corresponding particle in the quantum field theory, this forms of interaction describes the situation of the beta decay quite smartly. Okay? So the creation and annihilation are the fundamental property of the elementary particles. So the Fermi theory is one of the roots of the particle physics. Okay? At the same time, the Fermi theory provides a fundamental tool to analyze the weak interaction later. Okay. Another important achievement in the early 1930s is the Yukawa theory. The neutron was discovered in 1932. Then it turned out that the atomic nucleus has a structure of tightly bound proton and neutron. Okay, something like this. And in order to explain the binding force of the nucleus, Yukawa proposed the existence of the meson mediating the nuclear force in 1935. The mass of the meson was estimated as about 100 MeV from the size of the nucleus. This is because the range of the force is determined by the Compton wavelength of the mediating particle. The Yukawa discussed the force between the neutron and the proton. He considers that the force is mediated by the charged meson. And therefore, at the emission and absorption, the proton change to neutron, the neutron change to proton. Actually, when he considered this mechanism, Yukawa was influenced by the Fermi's theory. He adopted the idea that the species can change by the interaction. You can also try to explain the beta decay with this meson, something like this, but this was abandoned later. In 1937, 2 years after the publication of the Yukawa theory, a new particle was found in the cosmic ray. The particle has a mass similar to that of the Yukawa meson. So the Yukawa's theory attracted attention, but subsequent study of the new particle revealed that the property of the new particle interaction are not compatible with the Yukawa's theory. After some confusion, finally in 1947, the true Yukawa meson was found in the cosmic ray event again. The Yukawa meson is now called the pion, and the particle found in 1937, which is mistaken to Yukawa meson, is now called the muon. Okay. Hideki Yukawa was born in 1907 in Kyoto, Japan, and he graduated from the Kyoto Imperial University. And when he was a lecturer of the Osaka University at 28 years old, he proposed his meson theory. He received the Nobel Prize in 1949, and in celebration of Yukawa's Nobel Prize, Yukawa Institute of the Theoretical Physics was established in Kyoto University. Okay. Now, okay, so far we discussed about the three important works which can be regarded as the roots of the particle physics. Now we discuss the subsequent development of the particle physics. And the relativistic quantum field theory is a basic tool to describe the relativistic particle phenomena. And Dirac derived the existence of antiparticle from the Dirac equation, but this is not a field theoretical approach. Okay. Dirac's argument is asymmetric, not symmetric, between the particle and antiparticle. And it can be applied only to the fermion, okay, an argument based on the Fermi statistics. So however, if we adopt the relativistic quantum field theory, we can argue that the existence of the antiparticle in quite symmetric manner between particle and antiparticle. We can also prove the spin statistic relation from the field, relativistic quantum field theory. These are the early success of the relativistic quantum field theory. Okay, these two. However, once we include the interactions the field theory faced with a serious difficulty, namely when we calculate the higher order effect of interaction, there appears the divergent integrals. Before discussing the struggle with the divergences, let me remind you that the fundamental interaction which you have to think over. The electromagnetic interaction is a familiar one and important interaction. In addition to this, there are two interactions which are important in the particle phenomena. One is the wake interaction, which we discussed in connection with the Fermi theory, and the other is the strong interaction. This is just discussed by the Yukawa theory. We also have the gravitational interaction as a fundamental interaction, but its effect is very small, so that we discard the gravitational interaction for the moment. Now we come back to the problem of the divergence. Since time is limited, I would not enter the detail that the difficulty of the divergence was finally escaped by the so-called renormalization theory. And this theory, all the divergence absorbed into a few number of the parameters. Absorb means that the cancellation takes place between those divergent higher order contribution and the bare parameter, so that the observed parameter can be made finite. This is the basic idea of the renormalization theory. The renormalization theory was developed first in the electromagnetic interaction. The renormalization theory of the electromagnetic interaction completed to the end of the 1940s by the Tomonaga, Schwinger, and Feynman, and others. Yes. In Japan, Tomonaga and his group tackled this problem and made a great success. However, due to the World War II, they were isolated from the Western world, so that they developed their work independently from the Western world. Their works came to known to the Western world only after the war. Yeah, anyhow, the Nobel Prize was awarded to Tomonaga, Schwinger, and Feynman for their contribution to the renormalization theory of quantum electrodynamics. Okay. Tomonaga, Shinichiro Tomonaga was born in Japan in 1906. He graduated from Kyoto University, and it's well known that the Tomonaga and Yukawa were classmates in Kyoto University. And after graduated from Kyoto, he belonged to the Nishina group in Riken, and then moved to Tokyo University of Education. The work on quantum electrodynamics were done when he was there. And his interest in physics is quite broad, and he is also known for the Tomonaga-Rattinger liquid, for example. As I said, he was awarded the Nobel Prize in 1965. The renormalization method of the electromagnetic interaction could not be simply applied to the weak and strong interaction. For example, the Fermi interaction causes the divergence stronger than the electromagnetic interaction. So we had to wait another 20 years before the renormalization theory of the weak and strong interaction were available. In the early 1970s, de Hooft and Bertman proved that the so-called non-abelian gauge theory is also renormalizable. Here I do not enter the detail and just mention that this discovery of the renormalization of the non-abelian gauge theory enabled us to describe the weak and strong interaction in a renormalizable manner and provide a basic frame of the so-called standard model of the elementary particles. In the standard model, the strong interaction is described by the QCD theory, which is a non-abelian gauge theory based on the SU3 gauge groups, and the electromagnetic and weak interaction are described in a unified manner by the gauge theory based on the SU2 times U1, which is called the Weinberg-Salam glacial theory. Okay, here we see some names. Abdus Salam, he was born in 1926 in Pakistan. He moved to Cambridge in 1946, and he obtained a PhD from Cambridge University, and he returned to Pakistan from 1951 to 1954. But then he went back to England and became a professor of the Imperial College London. In 1997, he shares Nobel Prize with Gresham and Weinberg. And this connection I should mention that in G's development, particularly in building the Weinberg-Salam glacial theory, the notion of the spontaneous breakdown of the symmetry was very important. When certain continuous symmetry is spontaneously broken, the so-called Numb-Goldstone particle will appear. The Numb-Goldstone particle as a massless particle. And in the case of the gauge symmetry, G's massless particle will disappear and the gauge boson will get masses. This is called the Higgs mechanism. And Numb developed the theory of the spontaneous symmetry breakdown very much, and he was awarded the Nobel Prize for this contribution in 2008. Yoichiro Numb was born in Japan in 1921, and he was graduated from Tokyo Imperial University. He joined the establishment of the Osaka Metropolitan University as the first professor in 1950, where he studied the theory of the new particles. And he moved to the United States in 1952. And first he belonged to the Princeton and then moved to Chicago. Okay, new particle. Now, I'd like to turn to the discovery of the new particles. Okay, these are the elementary particles having appeared so far. The proton and the neutron are the particle composing the nucleus, and the pion is the particle predicted by Yukawa, which mediate the binding force of the nucleus. The electron is the most popular one, and neutrino is the hypothetical particle introduced by Pauli, and the muon is a particle no one requested. As I said, it was mistaken for the Yukawa meson at first. Eventually, it turned out that the muon is quite similar to the electron, except its mass. The mass of the muon is about 200 times heavier than the electron. Okay. Okay. Among them, the proton, the neutron, and the pion are the strongly interacting particle, which are called hadron. They undergo the strong interaction. And the electron, the muon, and the neutrino are called the lepton, and and they do not participate in the strong interaction. More or less, this was the situation at the end of the 1940s. In the early 1950s, however, many new particles were discovered. Okay, something like this. They all belong to hadrons, and those new particles are called strange particles. The strange particles brought us many things. Now we can say that from the discovery of those new particles, a new stage of the particle physics started. One of the new things brought by strange particle is parity violation. The discovery of the parity violation started from the puzzling fact concerning the K meson. One of the strange particles, K meson is one of the strange particles. At first, the K meson was given two names according to its decay mode. Those decay in two pions are called theta, and those two 3 pi ions are called tau. And theta and tau have almost the same mass, so this suggests that they are the same particle. However, the final stage have opposite parity in 2 cases. This state has even parity, and this state has odd parity. So this fact implies that the theta and tau have opposite parity, and therefore they are different particles. However, this last statement is based on the assumption that the parity is conserved. In 1956, the 2 Chinese scientists, Tsundao Li and Chen-Yin Yan, pointed out that the parity symmetry was not yet confirmed experimentally and could be violated. Soon after, in 1957, the Wu confirmed the parity violation with a famous experiment of the cobalt 60 beta decay. And distribution of the emitted electron from the spin polarized cobalt is asymmetric with respect to the direction of the initial spin. This does not happen if the system is parity symmetric. And Tsundao Li was born in Shanghai, in China, in 1926. And he went to United States and obtained a PhD under the Enrico Fermi at Chicago. He shared the Nobel Prize with Chen-Yin Yan in 1957. The Chen-Yin Yan was also born in China in 1922. He moved to United States in 1946. And obtained a PhD from Chicago under the Edward Teller. The work on the parity violation was done when he was at Princeton. The C.S. Wu was born in 1912 and died in 1997. And she was born in China and moved to the United States in 1936. She has got a PhD at Berkeley, California. And she carried out her experiment at Columbia University, where T.D. Lee was a colleague. After all, the parity violation was explained by the so-called V-A theory. In this theory, the particle participate in the weak interaction mostly through the left-handed helicity state, while the antiparticle do so mostly through the right-handed helicity state. Therefore, under the simple exchange of the particle and antiparticle, the system is not symmetrical. This is called C violation. So the C stands for the charge conjugation symmetry, which is invariance under the simple exchange of the particle and antiparticle. Therefore, the V-A theory is violating both P and C symmetry, but it's invariant under the CP, which is a combined operation of the C and P. Combined means that the space inversion P and the exchange charge conjugation C are done at the same time. So at this stage, it was thought that the CP symmetry is still preserved. However, it was found that the CP symmetry is also violated by the experiment done by the cloning featured trial in 1964. What they discovered is that the particle called K long decays into 2 pion, although it's a very small portion of the total decay. The K long is one of the strange particle, and it's a little bit difficult to understand why this process implied CP violation. But in short, if CP symmetry exists, K long should be the CP eigenstate, and the selection rule prevents to decay into 2 pions. More intuitively, the K long is a special particle which is a superposition of the particle and the antiparticle. And then if the weight of the superposition of the particle and particle are the same, the 2 contributions to this decay mode cancel each other. Therefore, the existence of the 2 pion decay implies that the weight of the superposition is different slightly. This implies asymmetry between the particle and antiparticle, and underlying physics law should violate the CP symmetry. Okay, anyhow, the discovery of the CP violation was a great surprise, and I'll come back later to how CP violation is explained by theory. Okay, now I have to a little bit hurry. Let us go back to another important development brought by the discovery of the new particles, which is a viewpoint of the compositeness of the hadron. Discovery of the strange particle implies that the increase of the number of the hadrons, so that it became difficult to regard all the hadrons as fundamental objects. It was natural to think that the hadrons have an internal structure, and they are made of fewer fundamental elements. An early work in this direction was done by Sakata. In 1956, he proposed a so-called Sakata model. And this model, it is supposed that the proton, the neutron, and the lambda particle, which is one of the strange particles, are the fundamental element, and just the hadrons, rest of the hadrons are composed of those 3 elements. The Shoichi Sakata was born in Japan 1911 and died in 1970. He graduated from Kyoto University, and he was a collaborator of the Yukawa in Osaka and Kyoto. Then he became a professor of the Nagoya University in 1942. And I was a student of the Sakata, but he passed away when I was a graduate student. Okay, accumulation of the data on hadron revealed that the Sakata model is incompatible with some of the experimental results, however. In particular, there are the baryons called sigma and xi, and the experiment shows that those particles share the property with p, n, and lambda. This was difficult to explain from the Sakata model because they should have the different structure. To cure these difficulties, Gelman proposed the so-called Koch model in 1964. In this model, the fundamental element are 3 kind of the quarks, U, D, and S. They are belonging to the different layer from the hadron in the sense of the hierarchy of the matter. And all the baryons are made of the 3 quarks, something like this, and including P, N, and lambda. The Koch model is working very well in many respects, but the Koch have a curious property of the fractional electric charge. Now, let me turn to my own work. I mean the work on the CP violation, which has been done by Masukawa. I would like to show our personal history first. Both of us graduated from Nagoya University and obtained a PhD also from Nagoya. And as I said, the Professor Sakata passed away while I was a student, so that I could not have much contact with him, but I enjoyed the atmosphere of the lab. Actually, the group was fairly large and quite active. Masukawa is 5 years older than I, and he was a member of the lab when I entered the graduate course. Okay, we started the collaboration soon. He moved to Kyoto University in 1970, and I also moved to Kyoto in 1972 after I obtained the PhD from Nagoya University. Then we resumed our collaboration and we wrote the paper on CP violation. Okay, now we come back to the physics. And as I said, in 1971, Hooft and Bertman proved the renormalization of the non-abelian gauge theory. And in particular, the Weinberg-Salam-Grashow theory account for the electromagnetic and the weak interaction in a unified manner. This was a situation when we resumed our collaboration. What we considered then was how to explain the CP violation in this framework of renormalizable gauge theory. Our conclusion can be summarized something like this. It's not possible to accommodate the CP violation in 3 or 4 Koch scheme. Let me remind you that the Gelman's proposal is number of the Koch is 3. The original Koch model, the original 3 Koch model has some flaw in the gauge theory, so that the 4 Koch model was already discussed, but 3 or 4 Koch model, 3 or 4 Koch are not enough to accommodate the CP violation. That is what we found. But, this means that the existence of the unknown particles, and we propose that the possible candidate of the CP violating model is a 6 Koch model. Okay, this is what we have done. I skipped some detail of this model. And after we propose this theory, discovery of the new quarks and the new leptons continued. In 1974, the 4th quark was discovered, and in 1975, the 5th lepton was discovered, and the 5th quark was discovered also in 1977, and so on. The existence of the 6th quark and the 6th lepton was established, but it's not enough to say that this model is correct. It was still necessary to test whether CP violation actually occur according to the 6th Koch model. This was done by a B-factory experiment at KK in Japan, in the SRAC in USA, California. The B-factory is an electron-positron collider optimized to produce the B meson. B mesons are heavy particles containing the 5th Koch B. Anyway, using the B meson produced at B factory and the Bell group at KK and the Baba group at SRAC proves that CP violation observed in the laboratory experiment explained by the six-coke model. Okay, according to these development, the so-called standard model was established. Let me summarize what is a standard model in one slide. In this model, the fundamental particles are the six quarks and the six leptons, which are the fundamental building block of the matter. And the three kinds of the fundamental interactions are described by the gauge theories. And the electromagnetic and weak interactions are described by the Weinberg-Salam-Grashow theory in a unified manner. And the strong interaction is described by QCD. I didn't explain much about the QCD, but Professor Gross played a leading role in the establishment of the QCD, and the Nobel Prize was awarded to him for this achievement. So you may hear about the story of the establishment of the QCD from him. Okay, so far, how 20 minutes. Okay, so far I have told mostly about theoretical development of the particle physics. Using the rest of the time, I would like to look at the experiment of the high energy physics in Japan briefly. High energy experiment in Japan started late compared to the Western world. One of the reasons is that the building accelerator was prohibited for a certain period after the World War II. The building of the high energy accelerator started in 1971 when KK was established. It was about 15 years behind from the world trend. KK stands for the Ko-Energy Kenkyusho in Japanese. It's located in Tsukuba Science City, and tour to KK is scheduled in the day after tomorrow. Okay, the first high energy accelerator built in KK was the 12 GeV proton synchrotron, which was far behind of the front line of the world in energy-wise, but it has been operated until recently and made a unique contribution, in particular in long baseline neutrino oscillation experiment. The next accelerator built at KK was the Tristan, which was the electron-positron collider with a center of mass energy of about 50 GeV. It was the highest energy E plus E minus collider when it was completed in 1986, although the first place did not continue long. After 80 years operation, Tristan was converted to the B factory, and which is the E plus E minus accelerator, but the energy of the colliding beams are different. The performance of the B factory at KK is excellent, and finally it exceeded about the performance of the SRAC B factory. As we have already seen that the physics outcome from the B factory is also excellent. B factory is now under the reconstruction for the upgrade of the performance. Okay, another unique accelerator which started operation recently is JPARC. JPARC is an accelerator complex built in Tokai campus of KK, which provides various kinds of the secondary beams for the wide range of the application. Okay, another unique experimental contribution from Japan is Kamiokande and the Super Kamiokande, which is an underground facility located in Kamioka Mine in the central Japan. Kamiokande and the Super Kamiokande are the large water tank detectors, which originally aimed to observe the proton decay, but the first important achievement was the observation of the neutrinos from the supernova explosion in 1980. Now, for this achievement, the Masatoshi Koshiba was awarded the Nobel Prize in 2001. Okay. Another important outcome from the Super Kamiokande is the discovery of the neutrino oscillation, which implies that the neutrino has non-vanishing masses. This experiment was led by the Yoji Totsuka, and at first they used the neutrinos produced in the air by the cosmic rays. But later, more detailed observation was made by the neutrinos produced at the 12 GeV proton synchrotron in KK. And this is called the K2K experiment. And this experiment is now taken over by the JPAC. The neutrino produced at JPAC is now observed at Kamioka. And, this is called the T2K experiment. The aim of the T2K experiment is a detailed measurement of the neutrino oscillation. Okay, probably I have told too many things, but I think that it's sometimes necessary to look at the stream of the development of the science in the long time span. And you'll find that the progress of the science is sometimes rapid and sometimes slow. And usually the rapid phase is triggered by some kind of the breakthrough. Okay, for instance, when we wrote the paper on CP violation with Masukawa, it was such a rapid phase. It was a revolutionary period triggered by the discovery of the renormalizability of the non-abelian gauge theory. It's rather easy in such a rapid phase to make a contribution because there are many problems not yet examined. On the other hand, it's more important and difficult to make a breakthrough in this slow phase. Probably it requires deep thought and deep insight. So I suppose that you will experience the both phases in your future research career. In any case, you will have a good chance of making important contribution to your field of science, as far as you are continuing a meaningful challenge. So I wish you good luck. Thank you very much.
Thank you very much, Dr. Kobayashi. Now I would like to give the microphone to a mentor, Dr. Shigeki Sugimoto, Professor of Institute for the Physics and Mathematics of the Universe, the University of Tokyo.
Okay. Any questions, comments? Come on. You should have a question. Okay. Before making a question, please stand up and tell us your name and your country.
So thanks for a fantastic presentation. And I'm curious about
Could you tell us your name?
My name is Gaku Eguchi, so the first doctor student of Kyoto University. And I'm curious about the clock model. About you first suggest the Sakata model suggest that proton and neutron is not a fundamental particle. Who is the first person to suggest the proton and the neutron is not a fundamental particles?
It's a little bit difficult. As I said, that the accumulation of the experimental data implies that the Sakata model is not adequate to describe the structure of the baryon. So and at some level that all the hadron belong to the same should belong to the same layer. It's became evident from the experimental data. So I cannot point out a particular person to.
Okay, any other questions? Okay, please.
I am Sanvet Kolekar from Ayuka, India. Okay, my question is, does the standard model have room to predict a particle which can be a candidate for dark matter?
Probably that most of the player of the standard model are already discovered. So the dark matter may be some kind of the still unknown particles. So I don't think that there is room to explain the dark matter within the standard model, but we have many extensions of the standard model, such as the supersymmetric theories, like that. And those theory has a good chance to explain the dark matter.
Okay. Okay, please.
Hi, I'm Gaurav from Indian Institute of Science, India. So I have a question regarding Super Kamiokande. How did they know that the neutrino activity that was observed was from this supernova? I mean, were they able to actually detect enough neutrinos to get the direction from which they came?
どうだったっけ方向まで分かったですかね。岡田さんよろしいですかね。Mostly that the timing was important. That at the same time that the several number of the neutrino event occurred. So this was the most critical signal of the supernova event. I'm not sure that the direction was measured or not. Sorry, later I can.
Okay, any other questions? Okay, please.
As you said, the experiment, Shunchiro Tani from the Kyoto University, as you said, the experiment and theory couple the, how to say, they make a unified model like a standard models. But now it seems that experiment and cell is slightly different. They are moving slightly different divisions. And what do you think you can couple this experiment and cell is, or what we should do to unify the experiment and theory?
Actually, in the high energy physics, the theory and the experiment, actually, in the sense of the player, they are quite different. And however, so far the theoretical prediction is tested by experiment. That is a way of the development. But actually, recently, that theory goes too far, so it's quite difficult to the experiment for. But in the near future, we will have some result from the experiment at the CERN, LHC. So we hope that this provides us the good information for the theoretical argument. Is it just a
Yes.
Okay.
Okay, any other questions? Oh.
Another question, many experiments are unified and result in standard model. And what do you expect? What kind of division of physics is unified in future? In case of particle physics, they follow a standard model. But what kind of division can be unified?
From the theoretical point of view, that the most important problem not yet solved is the quantum theory of the gravitation. And we have, how do you say that in so-called the string theory or something, those theory developed from the string theories are a good candidate for the quantum theory of the gravity. And those theory must include the other interaction too. So hopefully the development of this direction will unify all kinds of interaction and all kinds of the matter. Probably this is the most of the particle physicists expect.
Is there any chance that particle physics is unified with other physics?
Other physics? I don't understand the unified and other physics. As far as the fundamental interactions are concerned, that those things when particle physics are discussing is the completely account all the phenomena. So for example, the condensed matter physics is may be explained at the fundamental level by this particle physics concept. Okay.
Thank you very much.
Okay. Please.
Okay, my name is Geng Chong from China. So I want to ask, can you give us the description of the future of the particle physics as we know, in our the Earth, with the RHC or the Atlas, the energy have been achieved to about 14 TeV. So I want to know the future of particle experiment for theory or experiment. The future of the particle physics in experiment. You know, the RHC can have achieved the very the largest energy now, the 15, or now it's 7 TeV, and the future maybe in 2 or 3 years is 14 TeV. And can you give us the idea of the description of the future of particle physics?
Actually, so far we don't know what LHC will find, and so it depends on the result of the LHC experiment. And if we find some hint to the new kind of the physics from the LHC, then that we completely new stage of the particle physics will start then. And if they don't find anything, then I don't know what happened.
Okay, last question. Okay, please.
Okay, hi, Professor. Order to get a lesson from you. I'm Liu Zhiqi from Singapore. So I just ask a more risk question. Have your papers like ever been rejected by some high quality journals before you got this Nobel Prize? And how do you think the rejection of paper? How do you think of these things? Because especially now most of us are these young researchers. So how do you think about this one? Again, maybe
sorry. Yeah.
Okay, just I did. So have your papers ever been rejected by any high quality journals before you got this Nobel Prize? your papers being rejected. Yeah. How does that? Maybe again.
I don't think so.
Can I say again? Speak again. Have any your papers being rejected by some high quality journals before you got this Nobel Prize? Because most of us now are young researchers. So how do you think about these kind of things?
Sorry,
Whose paper did you say? Whose paper you mentioned?
I mean, your paper. Your papers, before you got this Nobel Prize, did you got some rejection from some high quality journal? Because usually for us young researchers, when we submit one paper to some high quality journal, we will always get a rejection and again. So how do you think about these things?
Sorry.
Their paper was not rejected.
So I think that the question is, have your papers ever been rejected from a high-profile journals, and how these affect your career or so on? I think that this is what you meant, right?
Okay. So why did you write submitted to the progress? Is that the question? Essentially.
Their paper was not rejected, so
So the question is so from time to time, papers are being rejected from high-profile journals, and this guy, he asked about how do you think this affects young researchers, and how should we treat this kind of events?
I don't know. I don't know what to answer. Sorry.
Okay, unfortunately, time's up. So.
Thank you very much, Dr. Kobayashi. Please give him a big hand to extend our gratitude. And thank you very much, Dr. Sugimoto. And thank you very much for all the questions. Now we would like to move on to the next lecture. Please welcome Dr. Hideki Shirakawa, Professor Emeritus of University of Tsukuba and Nobel Prize Laureate in Chemistry in 2000. The title of the lecture is Discovery and Development of Conductive Polymers. Dr. Shirakawa.